When two monolithic applications communicate, a hard-coded static IP address is sufficient. But in a containerized environment, instances are ephemeral. If a sudden spike in traffic causes the target service to autoscale into a swarm of new nodes, that hard-coded connection violently snaps. The client is left routing requests to an IP address that either no longer exists or lacks the capacity to handle the load. The traditional fix for this was DNS. You query a service name, and the DNS returns the active IP addresses using SRV records. But DNS relies heavily on caching. Operating systems and client libraries routinely ignore low time-to-live configurations, holding on to stale IP addresses long after a container has been terminated. The result is traffic routed into a black hole. Resolving a logical service name to a set of healthy physical IP addresses requires a system that updates in real time, completely bypassing the delays of DNS caching. To build this system from scratch, we need three distinct pillars: a highly available registry to act as the central catalog, probabilistic failure detection to continuously verify node health, and dynamic proxy routing to direct traffic without requiring application restarts. Moving from static IPs to these three dynamic systems separates the routing logic from the application code. It allows the infrastructure to adapt to continuous deployments and host failures automatically. The first component is the service registry. This is a distributed database that acts as the single source of truth for the cluster. Instead of hard-coding locations, service instances actively push their addresses to this central catalog. When a new instance boots up, it turns green. When it shuts down cleanly, it deregisters itself and turns gray, removing its address from the available pool. Having a centralized catalog solves the data problem. But it introduces an architectural dilemma. How exactly do the hundreds of microservices in a cluster query this registry to make their routing decisions? In client-side discovery, the calling service queries the registry directly and runs a local algorithm to establish a direct connection. This eliminates network hops, but it tightly couples the application to the registry, requiring custom SDKs for every programming language deployed across their fleet. The alternative is server-side discovery. Here, the calling service is completely unaware of the registry. It sends all traffic to a stable intermediate proxy, like an API gateway. The gateway queries the registry, selects a healthy backend instance, and forwards the request. This keeps the application code lightweight, but it introduces an extra network hop, and if the proxy fails, all communication stops. The registry centralizes the knowledge of service locations, but the topology you choose determines whether the application or the infrastructure carries the operational burden of routing. The registry is only useful if its data is accurate. If a node crashes without cleanly deregistering, the catalog continues routing traffic to a dead endpoint. This creates a gray failure, where the system appears healthy, but requests are silently dropping. The standard defense is a binary heartbeat. Nodes send periodic "I am alive" messages. If a message misses a strict timeout window, it's marked dead. But in a cloud environment, networks are unpredictable. Minor network jitter delays a packet by a millisecond, triggering a timeout and causing the registry to drop a completely healthy node. This leads to catastrophic false positives and unnecessary traffic rerouting. To fix this, modern registries use accrual failure detectors. Instead of a rigid binary state, these detectors output a continuous suspicion level based on the historical distribution of heartbeat intervals. This scatterplot maps heartbeat inter-arrival times against frequency. Early models used normal or exponential distributions, but both dropped to zero too early, missing the fat tail of delayed packets. The Weibull distribution specifically accounts for this fat tail, perfectly aligning with erratic cloud delays. The detector maintains a sliding window of recent heartbeats. By constantly analyzing the latest arrival times, it dynamically recalculates its suspicion parameters, adjusting its leniency on the fly if the network degrades. This side-by-side bar chart compares the mistake rate of the exponential model against the Weibull model. By accurately anticipating standard network jitter, the Weibull detector reduces false positives by up to 80% in unstable environments. Applying probabilistic mathematics prevents chaotic routing churn. The system learns the difference between a temporarily congested network and a truly dead server. Accrual detection solves the accuracy problem, but checking health at scale introduces a new bottleneck. If a central registry has to individually ping 10,000 nodes every second, the control plane effectively DDoSes itself. Instead of relying on a central server, massive clusters handle failure detection using peer-to-peer gossip protocols, most notably variations of the SWIM protocol. In a gossip protocol, a node sends a direct ping to a peer. If unacknowledged, it asks neighbors to initiate an indirect probe. If these fail, the node is marked dead. This failure is gossip to peers, disseminating exponentially fast across the cluster. Because nodes check each other, peer-to-peer gossip decouples cluster size from health check latency. The network scales infinitely horizontally without overloading the control plane. Once the registry mathematically confirms a node is dead, we arrive at the final execution problem. How do we physically stop traffic from routing to that dead node without forcing the calling applications to restart and read a new config file? The modern solution is a service mesh. This architecture strictly separates the system into a control plane, which holds the registry state, and a data plane, consisting of high-performance sidecar proxies attached locally to every application container. The application only talks to its local sidecar, handling all routing. The control plane updates these proxies in real time using the Dynamic Envoy XDS protocol. The Cluster Discovery Service, or CDS, pushes logical groupings of backend services. Then the Endpoint Discovery Service, or EDS, streams the exact verified healthy IP addresses. Finally, the Route Discovery Service, or RDS, pushes HTTP routing rules to seamlessly alter traffic splitting policies. By decoupling the state of the system from the execution of the routing via XDS, the infrastructure reacts to network realities instantly. The physical endpoints update automatically, completely transparently to the application code. When we combine these three pillars, we get a complete life cycle. A new instance powers on and immediately uses the gossip protocol to announce its existence to its peers in the cluster. The central registry absorbs this gossip data, updates its catalog, and immediately streams the new endpoint configurations out to all the local sidecar proxies via the XDS protocol. As traffic flows, sudden network jitter delays a heartbeat, but instead of catastrophically severing the connection, the Weibull failure detector calculates the suspicion level, recognizes the delay fits the statistical model for temporary congestion, and suppresses a false positive. Routing remains stable. This integration of a real-time catalog with mathematical failure detection automates the recovery cycle across the entire cluster. It ensures that your applications never route traffic into a void, replacing the fragility as static configuration with continuous, probabilistically verified consensus.